maxes and mins and extreme values of functions. Okay, so let's talk about what an extreme value is. Anybody? If you live in the Antarctic, it's extremely cold, right? So that means it's the extremely low temperature probably on the planet, right? So extreme values of functions are maxes and mins. Your book has this great example. I don't know how realistic it is, but it talks about, nice bell. It talks about how you can maximize your miles per gallon when you're driving your car. And they give us a function called m, which is miles per gallon. And then the x is the how fast you're going, the velocity, right? So they're giving us a cubic function, and they're saying that we might be able, if I tell you how fast I'm driving, I can tell you what your car's miles per gallon is, what your fuel efficiency is. Now, that's not necessarily realistic, but so if we wanted to know what speed we need to drive to get the best gas mileage, that sounds to me like a high point, doesn't it to you? That sounds like a maximum. With today's technology, what's really cool is that we can graphically look at things on a calculator. But back in the day, I didn't have this wonderful TI-89 where I could set the window, right? And then I could put the graph right up there. And so this is the cubic, M of V, right? With n positive n behavior, and it's a cubic, so it might have a high and a low. And here, I've got it graphed as a high point. Well, you might say, well, gosh, Mrs. Muller, why do we need calculus? I can just graph the function and find its maximum, right? By doing what on the 89? Hitting F5, and number 4, right? Yeah, and so we can find the maximum. And let's see what the maximum states here. It says that if we drive 38.6 miles per hour, we'll get 32.1 miles to the gallon. Now, well, it's pretty good, except who in this universe wants to drive 38.6 miles per hour, especially if you have a bumblebee vehicle like I do, right? Certainly not. But you see how as I go faster in my car, the miles per gallon go down. The fuel efficiency goes down, right? All right, so you might say, well, why on earth do we need calculus? Because I can calculate it this way. Well, we didn't have the nice calculators to graph. So something interesting is going on in our graph here at the high point. What kind of tangent line do we have? We have a zero sloped tangent line at the high spot. And we would also have a zero sloped tangent line at the low spot, right? So using calculus, what can we do? We could take the derivative and set it equal to 0 because the derivative represents all the slopes. And we can find out when the slopes were 0 and then plug in that x value that you found and put it in the original and find out what the max was, right? Well, that's what we used to do to find maxes and mins because we couldn't have this nice instantaneous graph to look at. And I'm really happy for you guys. I'm sad for me because it would have been so much cooler to learn it this way, I don't begrudge you any of that, I promise. All right. So it's eventful and helpful for us to study how we can find maxes and mins because in life there are so many things that are driven by maxes and mins. We want to maximize our profit and minimize our costs. And part of minimizing cost would be if I have I'm manufacturing, let's say, a can, I want to use the least amount of material, right? Because material is what costs something, right? And that's a minimum, right? And so minimums and maximums occur all the time, and so it's good to learn these things. Absolute extreme values are maxes and mins on a curve. We know what those are, right? Those are absolutely the highest values and absolutely the lowest values. And we learned that in honors pre-calc, right? No big deal. They're also called global extremes. So you might hear the word find the global maximum, and that just means the same thing as absolute, okay? They're also called extrema. That's plural for extremum. Anybody in here really good with Latin?
Father Tron.
Father John, people here? Oh, I don't know. There we go. No, she's just blessing herself.
I'll say when I see her walking around the hall, it's Father Tron.
Right. Anyway, extrema is the plural of extrema. And you've heard that word before in honors pre-cal because you had the best honors pre-cal teacher ever, right? Saved by the bell.
That's not us. Wait 10 minutes.
I know, but you didn't have to comment on my saying what a great pre-cal teacher I might have been. You guys were saved by the bell. Yes, okay. All right. So let's look at some examples here. This is the simplest function, right, that has some extrema to talk about, right? Y equals x squared. And its domain is all real numbers. This function, as we all know, has an absolute minimum at x equals 0. Does it have any absolute maxes? No. So we know that this one has an absolute minimum and an absolute maximum. And what's going on at that absolute minimum? You got a slope of 0. Yes. All right, what happens if I restrict the domain, though, to a closed interval? So I've got this x squared, which is a continuous function, and I've restricted its domain from 0 to 2. I have some absolute extrema, don't I? I have an absolute min at x equals 0 and an absolute max at x equals 2. All right, well then what happens if I have one of the ends open of my interval? I have an absolute maximum, but do I have an absolute minimum? Because could we play that game that I can name a number closer to 0 than you can? Like if I said I have 0.1, Andrew, what would you say? You would say that, and Matthew?
0.00.
Right, and then Mr. Bolger? You see how we would get to this thing, and everybody would get closer and closer, and nobody wins. And we could go around in circles all day and all night. So this is no minimum here, and no absolute or an absolute maximum. But if I were to ask you if this is bounded, what would you say? It's bounded, but it has no minimum. What about both open? Nothing. We have no extrema here, even though it looks like we might. All right. No minimum and no maximum, which leads us to one of the big 6 theorems in calculus called the extreme value theorem. That means if you have a function that's continuous, like our example x squared, and it's continuous over a closed interval, then you are guaranteed a maximum or a minimum. That doesn't mean if you have an open interval that you might not have. You see what I'm saying? It doesn't preclude you from having an extrema if you have an open interval. But with a closed interval on a continuous function, you are guaranteed to have an absolute max and an absolute minimum. Okay? So that's one of the big 6 in calculus. It's continuous, closed interval, and does it say anything about being differentiable? The answer is no. So it doesn't matter if it's differentiable. You're going, phew. All right, so let's look at this first curve here. And I have a closed interval. And where is my absolute max? On the left upper here. And then the absolute min is the lower point here. This is the absolute max and the absolute min occurring on the interior of my function, right? What is the left endpoint then? It's a local or relative minimum, and the right endpoint is a local or a relative maximum. Very good. All right, what about this function? On this closed interval, it's continuous.
Maximum minimums are at the endpoint.
The max and the mins are at the endpoint. Endpoints, yes. What about here? Don't look at it. Absolute max is in the interior, and then the absolute min is on the left endpoint. But what is the right endpoint here? A relative minimum, right? Got it? All right. So local maximum is the maximum value with in some interval, and the minimum would be the smallest in some interval. Okay, so here's the wild and crazy function. Can you tell me where its absolute maximum is? At the highest point there, that's a cusp. It's not differentiable, right? Can't take the derivative because it's not a smooth point. What about the absolute minimum? It's going to be on the left endpoint, right? So this is the absolute minimum. It's also, in this neighborhood, could you say it's a local?
Yes.
Or relative? Yes, you can. So local absolutes are also local. This would be a low. The next high spot is a local maximum. The next low spot is a local minimum. And then we have the absolute maximum, which is also local. And then a relative or local minimum. Locals are also extremes, okay? Notice, what's happening at the high and low spots? What kind of slope do we have? We have a zero slope there, and then, whoops, I'm sorry, and then no slope. Well, that's right, no slope. It's undefined. We call those critical points. Critical points occur when the derivative is equal to 0 or undefined. And extreme values can occur when the derivative is equal to 0 and when it's undefined. So I'm going to go to critical values here, okay? So we're going to come up with a definition here of a critical point. That's when the derivative is equal to 0 and the derivative does not exist. Those are the places that we need to check out for extrema, okay? Just because the derivative is equal to 0 doesn't mean that it has to necessarily be a minimum or a maximum. You can have a point of inflection there. Okay, like x cubed. I'll show you why. All right, so here's an example really quickly. Let's say we look at the function f of x equals x to the 2/3 on a closed interval. This is a power function. The first quadrant is yes, looks like the square root. The other side is even, right? So it's even symmetry. So it's like the seagull function, I like to call it. And so it's continuous, and I've got a closed interval. So where could the extrema occur? At the endpoints or at a critical point in the interior? So we have to figure out what the critical points are by taking the derivative. Of course, this calculus got to take the derivative. So we get 2/3 x to the minus 1/3, and then we put things where they belong because Mrs. Muller doesn't like negative exponents. And then we find out that the derivative is 2/3 times the cube root of x. Is this ever 0? Never 0, but it is undefined when x is equal to 0. So 0, 0 is a critical point. So I need to test out 0 at -2 and then 3. I have to check those points out as far as maxes and mins, okay? So I've got to check the endpoint. So let's check the critical point first. What happens when I plug in x equals 0 in the original? You get 0. What happens if I plug in -1? I'm just going to on the other side of it. Get 1. If I plug in 1, you get 1. So what happens on either side? If I'm at 1, does that mean that has to be a minimum? Right? So that's a minimum. Okay, it's a global minimum. But let's see. What happens when I plug in the endpoint? -2? You're going to get, this is messy, the cube root of -2 squared, which is 1.58. And then you get, when you plug in 3, the other endpoint, 2.08. So which wins I am the highest? At x equals 3, right? That's the absolute maximum. What wins I am the lowest out of these 3 points? 0, okay? So I recommend that you do a chart where you do x and f of x like this. Where you put x here and you put your endpoints. And then you put your critical point here. And then we said that this was 1.58. And we said this was 0 and this was 2.08. And this is f of x here, right? So you know this is the max. This is the min. And how did you get from 1.5 to 0? You went down, so that makes this a relative max. Do you see that? So I do a chart. I should have done a chart on here, but hindsight is 20/20, right? All right, so we know the absolutes. And I did it on the calculator to show you the actual function, and analytically I have some notes here on how you do the rules here. Find the value of each critical point, and then you plug them in the original. We're not going to do the slopes yet, not the slope dance. The critical points are not always extrema. I'll give you a prime example here. X cubed. Its derivative is 0 here, isn't it? Because it's 3x squared. It's not an extrema. X cubed. That's undefined. Is that an extrema? No. So the critical points are what they give you as a pool of numbers to test. Does that make sense? There we go. Goodbye. I'm going to not be here, but I'll have a video for the mean value theorem. I need somebody to write down the questions that you have on the homework and email them to me. Okay?
Next Tuesday.
Yeah, next Monday. Somebody going to do the prayer for me?
I'll do the prayer.
Okay, thank you, Ted. And you guys will have a problem of the day when you walk in. Okay, and then you'll be able to watch my video after. That's going to be the lesson plan. All right?